So good morning. We were discussing molar specific heat capacity. What is meant by molar specific heat capacity? It is the amount of heat required to raise the temperature of 1 mole of gas molecules through 1 Kelvin. And we saw that there are two types of molar specific heats. One is at constant pressure and the other is at constant volume. And we saw the equation for molar specific heat at constant pressure and constant volume. Today what we are going to do is we will find a relation between the molar specific heat at constant pressure and constant volume, and also we will find a constant which is the ratio between these two and see where it is used. So that's what we are going to do today. So let us see the relation between CV and CP. Which is bigger, CP or CV? Do you remember which has a bigger value? CP or CV? CP will be always bigger than CV. Why? At constant pressure, the equation, first law of thermodynamics will be dQ is equal to du plus PdV at constant pressure. And the molar specific heat capacity at constant pressure is Cp. And at constant volume, the equation becomes dq is equal to just du because dV, the change in volume, is 0 at constant volume. So Cp is the molar specific heat at constant volume. Now, it is the amount of heat required to raise the temperature. So when the temperature rises, the internal energy rises. So at constant pressure, when we give some heat energy, a part of it is used to rise the temperature and a part is used to do work. PdV is the work done. So all the heat energy given is not used to rise the temperature. While in constant volume, all the energy which is given is used to rise the internal energy or temperature. So in which case we can easily rise the temperature? At constant volume. So at constant volume, we need to give lesser amount of heat to raise the temperature compared to at constant pressure. That is why at constant pressure, the molar specific heat capacity or the amount of heat required to rise the temperature is more than at constant volume. Therefore, Cp will be always greater than Cv. You have to remember this. Now let us find a relation between Cp and Cv. So let us take the case of constant volume. At constant volume, the molar specific heat capacity is Cv, right? So what is the form of the first law of thermodynamics at constant volume? At constant volume, dQ is equal to du. This is the form of the first law of thermodynamics at constant volume. And we know that Cv, the molar specific heat, is the amount of heat required to raise the temperature of 1 mole of gas through 1 Kelvin, where m is the number of moles, dt is the change in temperature, and dq is the amount of heat energy given. Now for 1 mole of gas, for m is equal to 1. That is 1 mole of gas. When we consider 1 mole of gas at constant volume, we can write here m is equal to 1. Cv will be equal to dq divided by dt. Or you can write dq as equal to Cv times dt. Right? Now compare this with the first law of thermodynamics. You have dq is equal to du, right? So I can write here instead of dq, du. Du is equal to cv dt. Now this is an important equation which you have to memorize. See what the equation tells. The increasing internal energy is equal to Cv into the increase in temperature. We know that the rise in temperature and the rising internal energy are directly proportional. And what is the constant of proportionality? Cv. The molar specific heat capacity at constant volume is the constant of proportionality. So that shows how the internal energy change is directly related to the temperature change, and this equation is valid irrespective of the situation. Like this equation is valid not only at constant volume, at any process, for any process this equation is valid. So you have to remember this equation. So what is du? Du is the change in internal energy. dt is the change in temperature. And Cv is the molar specific heat at constant volume. So this is an important equation which you have to remember. But our aim is to get a relation between Cp and Cv. So we got an expression here. Now let me consider at constant pressure. At constant pressure, to derive this equation, we will be using this equation. So let me put it as equation 1. We will be using it when we find a relation between Cp and Cv. Now at constant pressure, we have the first law of thermodynamics. dq is equal to du plus p dv. Where dq is the amount of heat energy given, du is the change in internal energy, P is the pressure, and dV is the change in volume. Pressure is a constant, so P stays like that. And PdV is the amount of work done at constant pressure. Now let us take this as equation 2. Now we will be later substituting instead of du, Cv dt. And now we have to find similar expression to substitute for dq and dv, pdv. So let us do that. For that, let me first consider at constant pressure, we have the molar heat of specific, molar specific heat at constant pressure is equal to the amount of heat required to raise the temperature of 1 mole of a substance through 1 Kelvin temperature. So Cp is equal to dq by mdt. The equation looks same, but this is at constant volume, this is at constant pressure. That's all. Now for m is equal to 1, which means for 1 mole of gas, this equation can be written as Cp is equal to dq divided by dt. Or you can write dq is equal to Cp dt. So this is for constant pressure, and we will be using again this expression to substitute in equation 2. So let me note it as equation 3. Now what is remaining? PdV is remaining, right? Now for PdV, let us consider the ideal gas equation. Do you remember the ideal gas equation? What is the ideal gas equation? Who can tell me the ideal gas equation? By ideal gas equation, PV is equal to nRT. You have learned it like this, where N is the number of moles. P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant. Do you remember the value of R? What is the value of R? R is equal to 8.31 joule per mole per Kelvin. So these are quantities which you have to memorize. So memorize this. This is the ideal gas equation. PV is equal to nRT. T is the absolute temperature, which means temperature in Kelvin. Now here in this equation, in order to get dV, what I am going to do is differentiate throughout this equation with respect to temperature. So I am going to take d by dt on both sides. So this equation will become d by dt of PV is equal to d by dt of RT at when n is equal to 1. That is for 1 mole of gas. We consider all here for 1 mole of gas. So for n is equal to 1, this will become PV is equal to RT. So what I have done is I am taking differentiation with respect to temperature on both sides of the equation. Now P is a constant. We are considering a constant pressure. So P will come out. So it will become dV by dt. And this is equal to R is a universal gas constant. So it can come out of the derivative R into dt by dt. What is dt by dt? What is dt by dt?
1.
1. So this will become 1. So P dV by dt is equal to R. Now, if I take dt to other side, it will become P dV is equal to R dt. So, we got all the terms. Now, we can substitute in this equation. So, this is equation number 4. So, put from equation 1, 3 and 4 in equation 2. So, substituting from equation 1, equation 3 and equation 4 in equation 2. So I'm going to substitute this value and this value in equation 2. So it will become instead of dq, Cp dt is equal to instead of du, Cv dt plus instead of PdV, we have RdT, right? So dt comes throughout, so we can cancel it out and the final equation becomes Cp is equal to Cv plus R, which is usually represented as Cp minus Cv is equal to R. So this is the relation between the molar specific heat at constant pressure and at constant volume. So is this clear to you how we derive the equation Cp minus Cv is equal to R? So that's the equation. Is it clear?
Yes.
It's clear. Should I repeat?
No, it is clear.
Okay. So you have to remember this equation that the relation between Cp and Cv is equal to Cp minus Cv is equal to R. See, always Cp is equal to Cv plus R, which means Cp is bigger than Cv. So also by equation, you can show that Cp will be always bigger than Cv because we know that R is a positive quantity which is a constant value and it is 8.31. So R, look at R, it has the same unit as that for molar specific heat capacity, joule per mole per Kelvin. See molar specific heat capacities, it has energy, heat energy in joules divided by number of moles, okay, and change in temperature, Kelvin. So this has the same unit as of Cp and Cv. So I hope this is clear to you. Now let us see the ratio between the specific heats. The ratio between two specific heats, Cp and Cv. So first we consider this. Now we are going to learn the ratio between Cp and Cv. Now the ratio between Cp and Cv is expressed by the symbol gamma. Gamma is equal to Cp by Cv. Now let us see what is the significance of this quantity gamma. That is the ratio between Cp and Cv. For that, let us take the case of gases. So monospecific heat capacity are usually discussed when we discuss gases. When we are discussing liquids, we usually refer to specific heat capacity. That is per kilogram. That's the only difference. When it is monospecific heat capacity, it's very hard to weigh gas. So we take moles per mole. That's the only difference. So let us consider three types of gases: monoatomic gas, diatomic gas, and polyatomic gas. What is meant by monoatomic gas? Can you tell me what is meant by monoatomic gas? Mono means one.
One.
If there is only one atom in the molecule of a gas, you can call it monoatomic gas. Can you tell me examples for monoatomic gas?
Hydrogen.
Hydrogen is H2. It has
Oh.
two atoms, so it's a diatomic gas. One molecule is made of two atoms, right?
Helium.
Helium, yes, Majid, that's right, helium. Helium is an inert gas. So when you consider any inert gas, they will be monoatomic. They contain only one atom in their molecule. Okay? Now, let us consider the case of monoatomic gas. In monoatomic gas, so in monoatomic gas, the molar specific heat at constant volume is equal to 3/2R. So this is a quantity which you will have to remember. They may ask you in MCQ, multiple choice questions, what is the value of specific heat capacity, molar specific heat capacity for monoatomic gas, diatomic gas, polyatomic gas, and they will give you different options. So it's better to remember this value. Cv is equal to 3/2R for monoatomic gas. Now, once you remember this, the other things are connected. So with the flow, you can find all other values, but you have to remember the starting point. That is, for a monoatomic gas, the molar specific heat capacity at constant volume is 3/2R. Now we know that Cp, if Cv is given, it's easier to find Cp. Cp is equal to, from this equation, Cv plus R. So this will be 3/2R plus R. So 1R, I'm going to write it as 2/2R to simplify the fraction. So 3/2 plus 2/2, I will get it as 5/2R. So Cv is equal to 3/2, then Cp is equal to 5/2R. Then gamma. Gamma is equal to Cp by Cv, right? So this is equal to 5/2R divided by 3/2R. So by 2R gets cancelled and I will get, for a monoatomic gas, gamma is equal to 5 divided by 3. Try with your calculator, it will be around 1.67. It will go 1.66 like that, and when I truncate it to 2 decimal points, it will be 1.67. So this is a value for monoatomic gas. So monoatomic gas have a characteristic property that for all monoatomic gas, the value of gamma will be equal to 1.67. Okay, so the point is not visible, it's 1.67. Now let us consider diatomic gas. What is meant by diatomic gas? What is meant by diatomic gas? Gas in which the molecule has more than one atom. Can you give me example?
Hydrogen.
Yes, hydrogen, oxygen, nitrogen, they are all diatomic. There are two atoms in one molecule. So for diatomic gas, the value of CV is equal to 5 by 2R. See, it's going starting from 3 by 2, CP will be 5 by 2. Here CV will be 5 by 2R. Okay, now without calculation, can you guess what will be CP? Can you guess what will be CP? It goes in an order. Starting from 3 by 2, comes 5 by 2. What will be CP? CV is 3 by 2. CP will be 5 by 2. Let's see. So CP is equal to CV plus R, which means 5 by 2R plus just 1R. I'm going to write it as 2 by 2R. So this is equal to 7 by 2R. See? 1R. You just have to add 1. So this is 7 by 2R. Now gamma is equal to Cp by Cv, right? That is equal to 7 by 2R divided by 5 by 2R. So by 2R gets cancelled. You will get it as 7 by 5, which is equal to 1.40. So this is the standard value of gamma, which you have to remember. So for a monoatomic gas, all monoatomic gases, gamma will be equal to 1.67. For all diatomic gases, gamma will be equal to 1.40. Now, let us consider polyatomic gas. Okay, for polyatomic gas, what is meant by polyatomic? What is meant by polyatomic gas? Gas molecules which have more than two atoms in their molecule are called polyatomic gas. And for polyatomic gas, CV is equal to 3R. See, it's not a fraction. It's not a fraction. CV is equal to 3R. Can you give me examples for polyatomic gas? Can you give me examples for polyatomic gas? Water vapor. What is the formula? H2O. There are 3 atoms, right? Can you give me like that some other? H2S, hydrogen sulfide. So all the molecules which have more than 2 atoms will be polyatomic gas. Now for polyatomic gas, CV is equal to 3R. So what will be CP? CV plus R, right? So that is equal to 3R plus R, which is equal to 4R. So what is gamma? Gamma is equal to Cp by Cv, which is equal to 4 by 3, and its value is 1.33. It will go on like that, 1.333. It will go on like that. So we have the value of gamma for monoatomic gas, diatomic gas, and polyatomic gas. It's better if to remember these values if you have good memory. Otherwise, you will have to derive and see. And the one of the important property of gamma is that it can be used to find out what kind of gas it is. If you have some gas, depending upon the value of gamma, you can find out whether it is monoatomic, whether it is diatomic or polyatomic gas. Is that clear to you? Is that clear to you?
Yes.
Okay, so these are the values of gamma, and you can use it to find out what kind of a gas it is. Now, another important property of gamma is that it can be used to find, one is this, and it can be, gamma can be used to find the velocity of sound. Velocity of sound in a gas. The velocity of sound in a gas depends on gamma. For example, the velocity of sound in gas V is equal to root of P gamma divided by rho. V is the velocity. What is P? It's gas. So P is pressure. What is rho? You're familiar with the symbol rho, right? Rho stands for the density of gas. So
Density.
V here is the velocity of sound. And P stands for the pressure of gas. And rho stands for the density. So P is the pressure, rho is the density, V is the velocity of sound, and it depends on, the velocity of sound depends upon gamma. Okay, so it depends also upon the type of gas it is, whether it is monoatomic, diatomic or polyatomic. So each one will have a different velocity. In each one, there will be a different velocity for sound. So this is another use of gamma. Now, gamma also appears in the different relation between the thermodynamic coordinates in an adiabatic process. Do you remember what is adiabatic process? What is adiabatic process? When do we call that a thermodynamic process is adiabatic? A thermodynamic process is called adiabatic if there is no exchange of heat between the system and the surroundings. So for an adiabatic gas, adiabatic process, there is no exchange of heat between the system and surroundings. And what are the thermodynamic coordinates? What are thermodynamic coordinates? Pressure, volume, and temperature. So we will be discussing the relation between these three quantities in an adiabatic change, and in all those relations gamma appears. So let me tell you how gamma appears in the different processes in adiabatic, in different relations in adiabatic processes. So first relation, which is between pressure and volume, PV raised to gamma equal to a constant. So this is a relation between pressure and volume in an adiabatic process. PV raised to gamma equal to a constant. And a second relation is that, okay, so this is between pressure and volume. Now what are the other quantities? Temperature and volume. So temperature and volume. TV raised to gamma minus 1 is a constant. And the third relation connecting pressure and temperature is that P raised to 1 minus gamma divided by gamma is a constant. So these are the three relationships between different thermodynamic coordinates for a adiabatic process. See, in all of them, gamma appears. So in next class, we will derive each one of these quantities. We will see how we can derive the expression P V raised to gamma is a constant, T V raised to gamma minus 1 is a constant, and P raised to 1 minus gamma by gamma is a constant. We will derive these equations in the next class. For the time being, you can just remember these equations, okay? Are you listening?
Yes.
Okay. So now let me also express CV, the molar specific heat at constant volume in terms of gamma. You know the expression that Cp minus Cv is equal to R, right? Now let me divide this throughout with Cv, because Cp by Cv is gamma, right? I want to bring gamma to this equation. So I am dividing throughout with Cv. So the equation becomes Cp by Cv is gamma minus Cv by Cv is 1 is equal to R by Cv. Or if I take Cv to this side, gamma minus 1 will go to the other side. So Cv is equal to R by gamma minus 1. So this is the relation between the specific molar specific heat capacity at constant volume and also gamma. So we saw that molar specific heat capacity at constant volume is an important quantity, and it depends upon the constants only. See, R is a universal gas constant, and for each type of gas molecules, gamma will be a constant. So Cv is a constant. So if we know Cv, we can come up with all other quantities. We can come up with Cp if we know Cv. We found that when we derived the equations for monoatomic, diatomic, and polyatomic gases. So Cv is an important quantity with which we can get all other related values. So Cv is equal to R by gamma minus 1. And also we saw that Cv is also a constant of proportionality that connects the change in internal energy and the change in temperature. So earlier we was telling that always the change in temperature affects the internal energy and they are directly related. So the constant of proportionality is Cv. So Cv is an important quantity which if you know for one particular gas, all other properties or all other constants can be obtained from that. Is it clear? Is it clear?
Yes.